In Lab 4, we examined the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. Some of the main concepts to refresh on include the momentum principle. If there's a change in momentum, there is a net force acting on the system. The energy principle, which we will expand on in this lab, and Hooke's law. The displacement is proportional to the deformation. The energy principle is the main concept of this lab. We can conclude that the change in energy is zero with the components of change in kinetic energy plus the change in spring potential energy plus change in gravitational potential energy. And below are the key breakdown formulas. After setting the calibration length, we can track the path of the spring mass, as seen here in Tracker. Our initial conditions include a starting time of 0 seconds, initial y at negative 0.35 meters, initial x at negative 0.115 meters, and an initial velocity vector at 0, 0, 0 since we started at rest. The initial mass was given to be 0.402 kilograms, and we know the force of gravity on Earth to be 9.8 meters per second squared. Here are the initial conditions written out. We know that t is the period of oscillation, and from Tracker we can calculate t to be 1.266 seconds. Using the formula 2 pi on the square root of m over k, t squared is equal to 4 pi squared times m over k. We can then rearrange to solve for the spring constant k and get 9.902 newtons per meter. We will revisit the oscillation period in the what does it mean section of the lab. We were given L equals 0.7 meters, so using the spring force formula, we then know that the spring force is equal to the force of gravity. From there, we can solve for L null to be 0.302 meters. I then inserted these constants into Glowscript. The link to the code is in the description below. Ultimately, the energy principle was satisfied. Here are snapshots of the final Glowscript outputs. Considering the change in kinetic energy plus the change in spring potential energy plus the change in gravitational potential energy, we see the correct oscillations in the diagram that satisfy all we have covered. Next, I made two separate estimates of oscillation periods by taking the maximum point on the x position graph in Tracker, then one for the y position data. By charting the time at the peak of the oscillations, I then found the time difference in oscillation periods. The x period and y period times were similar, and any discrepancies can be attributed to human error. All of this together sums up the energy principle.